At first, I would like to thank the organizers for the invitation. My Linux journey started 10 years ago from Ubuntu, so it feels really great to be here and be the part of this event. And just before we started, I'd like to know my audience better, so I'd like to ask you some questions. At first, please raise your hand if you heard about YTsaurus before. Yeah. Okay, and now please raise your hand if you heard about Apache Zookeeper before. Okay, and now please raise your hand in such a way that there are exactly 2 hands rising. No, the totally 2 hands in the audience raised. Okay, I see that you're a bit confused because this is a distributed coordination problem and they are hard. So hello again, my name is Grigory Reznikov, and today I will talk to you about how to use our system YTsaurus as a distributed coordination service. So what is our plan for today? At first, we will talk about distributed coordination problems and why are they hard, and what are already created solutions for these problems. After that, we will talk about YTsaurus, and then we will talk about some its subsystems, which can help us with the distributed coordination problems. And finally, we will talk about our open source journey. So let's begin. Imagine you being a distributed systems developer, and you have a bunch of servers, and you want to create a program that runs some assignments on them. And you add some scheduler, you add some worker, and you want this system to run just like one big computer. And when you're writing your code, you expect that the situation in the data center after your deployment will look somehow like that. There are servers, they know what are they doing, and everything works fine. And yes, it works fine until one day when some top of the rack switch is broken and we got network partition, and after that your program is running somehow like that. So you're getting some brain splits, something is not working, and you are running through the servers with SSH trying to understand what's going on. And this is not good because your servers are not working, and in the worst case, you lost your data, so you want to do something better. And after that, you learn that the problems that arise during the development are called distributed coordination problems. So here are some examples of distributed coordination problems, which are the problems in which a bunch of the servers involved, and they should work in some good way, passing the messages, working all together on your hard problem. The first one is as simple as service discovery, in which you just have a bunch of the servers and you want to find all alive servers in any moment. The second one is leader election, in which you have some servers and you want exactly one to be elected in any moment. So you elected a leader, and after the server with a leader is dead, another server will be elected as a leader. Another one is exactly one delivery, when you want to reliably send messages between your nodes. Also, there is a distributed throttler. When you have a bunch of the servers, you have some shared resource, and you want to make sure that servers as a whole do not acquire too much resource in a total. Also, there are many other distributed coordination problems, and they are all challenging. This is because servers sometimes fail. The network between servers is very unreliable. You can have duplicated packets, you can have lost packets, you can have network partitions, you can have all of this network hell. You can rely on clocks, and clocks are very unreliable because of the sleep second stuff, because of the clock skew, so never rely on clocks on distributed systems. Bugs which arise during distributed system development are usually tricky and hard to reproduce. So, you have a bug, it appeared once, and you will never see it again until it loses all your data. Here is an example of bug in our system, which inverted if was done incorrectly, and it could lose the data because of forgotten fsync system call. And fortunately, we found that out before data was lost. So distributed systems are hard, and after you know about the distributed coordination problems, you find out that there are specialized algorithms to solve them. For example, the famous Paxos protocol or the Raft protocol. And after that, you think, okay, now I'm smarter than before, so I will implement Paxos, and everything will work fine. You open the paper on Paxos, you read it, and you implement it, and it works until you realize that you're in the situation which is described in the picture. Like, distributed protocols are very hard, and it's usually not enough just to read a paper and implement them on a programming language that you like. There will be much data races, network races, and other bad conditions. So usually when people implement such protocols, they have spending much time stress testing it to find out all the bugs and making it work somehow stable. And these protocols are hard, and many developers have to solve distributed coordination problems in some way. So it will be cruel to expect from every big systems developer to understand in deep such hard things. So fortunately, we have systems that will help you to solve these problems, which are called distributed coordination systems. There are some frameworks that allows you to build distributed systems and not to think on many problems that usually arise during this development. However, you should still understand challenges that can appear in distributed world because they are not silver bullets. The three most famous systems of such a kind are Apache Zookeeper, etcd, and HashiCorp Consul. The Apache Zookeeper is, I think, the most famous one, and this is a reliable distributed tree-like file system which can be used, I don't know, for redirection, for two-phase commits, for storing the dynamic configurations of your system, and many others. You can find bindings for Apache Zookeeper on your favorite programming language. So this is a de facto standard in this industry for now. Another one is etcd, which is the key-value storage which is used in Kubernetes for coordination. This is more modern system that is written in Go, like I think 8 years ago, and it proved to be quite stable and reliable. And I think for now there is a trend of migrating from Zookeeper to etcd because etcd showed to me more stable and allows to store more data in the metadata storage. The third one is the HashiCorp Consul, which I think is less popular and mostly used for lead election and dynamic configurations of the servers. And now let me introduce the main character of my talk. The YTsaurus is a system that we are developing. Here is our nice mascot and stickers with whom you can find on the table there. So if you open our beautiful site, you will see that YTsaurus is open source big data platform for distributed storage and processing. And on the first glance, this is some systems for, I don't know, analytics, ML developers, people like that. But it also can be used for distributed coordination. And I will talk to you today how can we use it. Okay, and here you can meet our beautiful team, and you can see these happy people developing YTsaurus team and see a little bit scare in their eyes because of the years of distributed systems development. So these are the components which are used in YTsaurus, and yesterday my colleague Andrei gave a beautiful talk on YTsaurus in general, from which you can learn what is YTsaurus and how can you use it. And today we will be focused on two layers of the system, namely Cypress and dynamic tables. The Cypress is our distributed file system with support of transactions that is usually used to store some big data like tables, big files. However, it can be used in an Apache Zookeeper way. And another component are dynamic tables, which are low latency key-value storages and sharded distributed queues, which can be used for exactly one message passing and in etcd-like way. So now let's move closer to the Cypress. The Cypress is a tree-like file system. So you can see some objects stored here in a tree. You see some system objects like users and accounts, and you see some user objects like files or tables. And it actually looks like some classical Unix-style file system. There are paths which are separated by slashes, just like, I don't know, ext4 or xfs or some file systems like that. And as it used to be, it supports some basic commands which are inherent for tree-like file systems. I don't know, you can create new nodes, you can remove some nodes, you can copy some nodes. More than that, Cypress supports attributes, which are quite a nice feature. Each object in Cypress can be annotated with a set of attributes. And attributes are just named YTsons, where YTson is a JSON-like object. So for every object, you can store a set of attributes. Some of them are system. For example, the attribute type, it is set by a system telling that the object it's referring to is a table. And another one, for example, foo, is a user attribute, which is just attribute set by user. And it can be used, for example, for maintaining the dynamic configurations of your servers. You can just reliably store some small amounts of data just in a Cypress, which is similar to how you can store some attributes of nodes in Apache Zookeeper. More than that, Cypress supports transactions. Here you can see an example of how we can change an attribute inside the transaction. We have some node home/user, and we have some attribute called myAttr, which is equals to 42. After that, we start some transaction, and we set the value of the attributes inside the transaction. After that, attribute remains the same in a trunk version of a node that is outside of the transaction. And inside the transaction, the attribute is changed. So after that, we commit the transaction, and the attribute is changed. As usual with the transaction can be used to do multiple mutating actions atomically. So in YTsaurus, you can atomically within a transaction create, remove, copy, move, or modify some Cypress nodes. You can change the attributes. You can acquire logs, and we will use it later for leader election. In case if you're using YTsaurus not for distributed coordination, but also as a big data platform, within a transaction, you can write data to the tables, you can run a MapReduce query, you can write a YQL query, which is a SQL-like framework for working with the big data. And after you perform some actions within the transaction, you can either commit or abort it. And in case if you commit the transaction, all the changes that were performed within this transaction will be applied atomically. And in case if you abort the transaction, all of the changes will be invisible. So now let's see how can we use transactions for leader election. Suppose we have a bunch of peers and we want to elect exactly one out of them. We create some node which will be used for leader election. And being a leader means to be able to acquire an exclusive log on this node. So every peer tries to do the same. They start the transaction with some timeout. After that, that peer should ping the transaction via a specific call. And if it didn't ping the transaction within a timeout, it will be automatically aborted. After the peer started transactions and started pinging its transaction, it tries to exclusively log some node. In case of success, okay, you're a new leader until your transaction aborted. So this peer will be a leader, and eventually when this peer dies, it stops pinging the transaction, transaction becomes aborted, node becomes unlocked, and another peer can acquire an exclusive lock on this node and become a new leader. So here is a scheme of this algorithm. And now let's move to a more important thing. So what does it mean to be an elected leader? This is actually important because many people misunderstand the concept of external leader election with some black box systems like Zookeeper or etcd. So let me show it on an example. Okay, hello, my name is Grigory. I am a mayor of Riga. Please, everyone, give me €1 as a tourist fee. Anyone? Oh, well, I'm a terrible actor. So what is my problem? In the distributed systems, being a leader is tightly connected to be able to act like a leader. For example, if we consider some classical protocols like Paxos or Raft, you become a leader after you received a quorum of votes that you are a leader. But it's not also sufficient to become a leader by getting a desired number of votes. You also have to be a leader after that. And being a leader after election means to be able to act as a leader. And in case of Raft, it is actually being able to write something as a leader. And when you write something in a Raft, you have to make sure that a quorum of peers will accept your rights. So while you are able to write, and a quorum of peers still thinks that you are a leader, you are a leader. After you lose your quorum and they don't recognize you as a leader, you will not be able to write. And you will not be a leader. So why is this important? Suppose you use some system, I don't know, Zookeeper, YTsaurus, etcd, anything, to elect yourself as a leader. At some moment of time, you realize, okay, I'm a leader. And you're starting to act as a leader. For example, modifying data in some external system and doing something for which you created this leader election. And some time passes, and for example, you get a network partition. You are not able to ping your transaction in YTsaurus or in Zookeeper anymore. So this external system thinks that you are dead, and it elects a new leader. But you don't know about it because you are not able to reach a Zookeeper. So you continue working as a leader, and you have two leaders, a newly elected leader and you who did not realize yet that you stopped being a leader. And here you get some data race, which can end up with something bad. So to prevent these issues, in YTsaurus, there is a mechanics which is called prerequisite transactions. This may help in case if the mutating actions that you are performing as a leader is done also in YTsaurus, like not in some other external systems, like, I don't know, some Postgres, but also in YTsaurus. In this case, you can use a transaction in which you was able to exclusively lock election node as your leader list. So after that, every mutating actions you perform, you are annotating with this transaction. And these actions will be executed until your transaction is aborted. So for example, in the picture here, some peer started his transaction and was able to successfully exclusively lock some node. After that, this peer performs a write table action, and it is okay because his transaction is still alive. After that, something bad happens. He was not able to ping a transaction for some time, and the transaction becomes aborted, and maybe another peer was able to be elected as a leader. But our leader, again, still don't realize that he is not a leader anymore. So it tries to write table again and gets a failure because the transaction is already aborted. So while all of your mutating actions are done in YTsaurus, you will not have data races until you are using prerequisite transactions. And this is why YTsaurus can be quite convenient for multiple purposes, because you can not only do a leader election inside it, you can do much more things as with YTsaurus, because it is a big data platform. You can also store some data and process it. So you can, for example, write data to the table using prerequisite transactions. You can transform some data using MapReduce or SQLite queries using prerequisite transactions. Soon you will be able to write data to the dynamic tables using prerequisite transactions. So this is quite convenient because YTsaurus support multiple functionality. And now let's move on to another component of YTsaurus that can be used for distributed coordination problems. After all, YTsaurus is a big data storage, so it supports tables. And there are two kinds of tables inside YTsaurus. There are static tables, which are immutable and out of scope for today. And there are dynamic tables, which are mutable and allows modifications in some way. And now we will talk about them. So there are two kinds of dynamic tables in YTsaurus. There are ordered dynamic tables and sorted dynamic tables. The ordered dynamic tables are distributed sharded queues, and we will look how they can be used for exactly one message passing. And sorted dynamic tables are transactional key value storages with some natural conflict semantics. Let's start with ordered dynamic tables. Ordered dynamic tables is sharded distributed queues. The sharded here means that you have a number of shards, and each shard is an independent queue. And in each shard, you can store some number of messages, which can be appended, which can be read, and which can be trimmed. So the data structure can be used for reliable exactly once message parsing. When a sender wants to send some message to the receiver, it just adds a message to the queue. After that, receiver tries to read some messages from its mailbox, and at some moment of time, it realizes that, okay, there are some new messages. It reads it, it applies it, and after that, it can trim them. So you will have a guarantee that receiver will get each message that was sent by a sender exactly once. Another distributed coordination primitive which is used in YTsaurus are sorted dynamic tables, which are distributed key value storage with transactions. And this is quite similar to etcd. You can start a transaction, you can modify a bunch of keys within this transaction, you can commit this transaction, and logs will be checked. When creating a transaction in sorted dynamic tables, you can lock every key using a read lock or write lock, and you will have natural conflicts. Write conflicts with write, and read conflicts with write, and read does not conflict with read. Also, soon we'll have a nice feature which is called shared write locks, which allows you to write concurrently on the same key, and all of the writes will be linearized according to some global clocks of the cluster. This is quite a powerful tool, and this is used internally, for example, for our YQL agent, which is a subsystem which is responsible for running our SQLite queries. We have a bunch of workers, and each query should be assigned to some worker. So the controller of this assignment uses internally sorted dynamic tables to assign queries to workers. However, this is a quite complicated tool, so to use it efficiently, you have to spend some time reading the documentation to use it properly. Okay, and now let's talk a little bit about reliability. I believe that the most important property of the distributed coordination system is not a performance, but a reliability. You do not usually put a heavy workload on your Zookeeper or etcd or something like that. The most important is that you want it to be reliable. You want it, I don't know, to never lose your messages, to never elect two leaders, and to never do something wrong. It's better to have a downtime that doing some incorrect behavior. And I think this is the reason why Apache Zookeeper is so popular. It is being developed for, I don't know, 20 plus years. And during this time, it proved itself to be quite a reliable system. And now I came here and tell you, try some new platform which you never heard of. So actually, this is not true because YTsaurus is being developed for 13 years before, so it proved internally to be quite a reliable system. And this March we open sourced it, and I think it was a good move for our system. It became quite popular on GitHub. We have for now more than 1,000 stars. So it is not as no name as you may think. Also, to prove that we are reliable, we are planning to pass the YTsaurus test in the nearest future. The YTsaurus test is a framework for testing distributed systems. So, like every good distributed system, like Zookeeper, is being tested on YTsaurus, and we are planning to get a YTsaurus report telling whether we are reliable or not. Finally, we are always happy to meet some developers which are interested in distributed system or wanting to learn about distributed system. And here I prepared for you a free good first issue that require like less than 10 lines of code. So you can start playing with YTsaurus from them. You can try to do them, learn a little bit more about YTsaurus, about our code base, and learn how development in our system is done. Also, we have many like more big projects, for example, implementing a Zookeeper API or YTsaurus. And if you're interested in doing some big project in distributed systems field, you can contact us or on our GitHub or at the email on the slide. So that's it. And now let me tell a couple of words about how you can try it. The first one, you can go to our site, YTsaurus.tech, and book a free demo for an hour for the YTsaurus cluster. You'll get a fully functional YTsaurus cluster for an hour. You will be able to access it and to play with some simple examples. Also, yes, we are open source. We are open source with the Apache 2.0 license, so you can download our source code from GitHub and build it, or just get from a Docker registry our images and run your own YTsaurus cluster in Kubernetes or in some local version of Kubernetes like Minikube. And in case of any questions, join our community in Telegram, and we will be glad to answer all of your questions. So that's it. Thank you very much. Any questions?
So some other big data GitHub thing I've recently seen, or database thing, is SerialDB. Do you know it?
Sorry?
SerialDB?
MariaDB?
SerialDB, I don't know, whatever. I just wanted to ask what it's, in your opinion, is the biggest difference between this kind of table-like data storage and a more classical database system. So I'm not really much familiar with this distributed coordination system. So what's the biggest difference? Just
I guess the biggest difference between YTsaurus and other systems of Apache class is that you have everything in a single namespace. For example, in the Apache world, you have different systems for different purposes. You have Apache Zookeeper for distributed coordination. You have Apache Hadoop for MapReduce. You have Apache HBase for key-value storage. I don't know, and many others Apache products. And in case of YTsaurus, you have one cluster for every purposes. You can deploy it once and work with it in different ways. You can use it for distributed coordination. You can use it for data storage. You can process big data in it. You can train your machine learning models. You can run analytical queries and do multiple things all in a single cluster. So it heavily reduces the amount of work you have to do to administer it, because you have to administer one cluster and not 5 clusters of I don't know, Postgres, Zookeeper, etcd, Hadoop, and other things.
And maybe a second question, what's the origin of the name?
Oh, this is a hard question because when it was developed internally, it was called YT, and no one knows why it's called like that. However, if you want to open source something like YT, you will be in a trademark hell because there are multiple projects which are called the same. So we spent, I don't know, 4 months discussing how we should call it, and finally we came to the name YTsaurus, which seemed quite good for all of us.
How ready is it to use for now? Like you've been internally and now you're up open source. Do you have any problems with implementing your system for anyone outside? Like how ready you are?
Yeah, we have some companies which are trying to use it right now. We do not have any, like, I don't know, talks about some companies that adopted it and is using it successfully. However, we hope to get a few ones next year.